Okay, hi. Welcome back to another one of these excellence reps videos that we're doing in the lead up to the calculus papers. Okay, so I've got three excellence questions lined up for you. First complex, then differentiation, then integration. These were shared on Instagram yesterday, so hopefully you've had a go at them first. If not, then I'd recommend that you pause, give it a try, and then come back and have a look at the answer that I've done. Okay, anybody that happens to hop on live, say hello in the chat, and then I know that you're there. I can check for any questions that you might have along the way. All right, now the three questions today are some fairly standard ones that we would get from for excellence questions. So I'm quite happy with the ones that were off of this past paper. And this starts with actually a really lovely one from complex numbers, where we are finding the solutions to this situation of what k needs to be in this equation so that we have the equation itself with no real roots. So that means instantly you should be thinking about the discriminant. That's how we can tell what type of roots we have. Okay, so let's start with this equation here. I'm going to take the square root over to the right-hand side and then square both sides to get rid of the square root. So if I was to do 6 plus x squared, that's going to get rid of that bit there and square the 4 as well. So we end up with 36 plus 12x plus x squared is equal to 16 times 3, which is 48x plus 16k. Let's just get the calculator at the ready. Now, rearranging that so that it's a kind of normal looking quadratic, we're going to get everything over to the left hand side. So that will give us x squared. We can take the 12 and minus the 48 for the x's, and that's a minus 36x. Then we have the 16k. That's going to come over to the left-hand side. So this will be plus 36 minus 16k, like so. Now, for there to be no real roots, this means that the discriminant, b squared minus 4ac, has to be less than 0. Excuse me. Okay, so for that quadratic there, we're going to pick out the pieces that make the discriminant. So b squared minus 4ac, well, the b part is the minus 36, so we have that squared. The minus obviously will become positive when we square it. Minus 4 times a, which is 1, that's from the coefficient of the x squared just there. And the c part is anything that's constant, so it's this bit just here, 36 minus 16k. So that comes to 1,296 minus, now multiplying out that bracket, 36 times 4 is 144, and 16 times 4 is a plus 64, because we've got a minus times a minus, and that's got a k. Now, checking for the discriminant to be less than 0 means we're going to add on a less than 0 at the end there. Now, 1,296 take off 144 is 1,152 plus 64k, less than 0. So k is going to be, if we take that over to the right-hand side, it'll be minus 1152, and then we'll divide it by the 64. So k has to be less than negative 18. And we are done. A lovely excellence question, and I'm just looking up the mark scheme so we can see where you got other marks in there. So this third line here, that bit getting to that point, that's a merit. They didn't specify a particular place where you could get achieved out of this one, but that's where you can get a merit. Okay, and if there's no questions on that one, I will move on. If you do have any questions, just pop them in the chat. I'll pause, I'll go back to whatever it is that you want to take a look at. Okay, differentiation. We have a spherical balloon, a very typical situation for rates of change. It's being inflated. We are given that it's increasing at a constant rate of 300 cubic meters per second. So I'm going to start by writing that down. Always start by writing down the rate you've been given. So this is how the volume is changing over time, and that is a value of 300. We've got the balloon has limited strength. It'll burst at some point, and that point is when the surface area reaches 7,500. We want to find the rate at which that surface area of the balloon is increasing. So our thing that we want to find is dA by dt. So how much is the area changing over time? When it comes to rates of change, I always start with those two pieces. What's the thing that I have, and what's the thing I want to work out, written as rates like this. Then I can figure out how to link the two. So if I was to do dA by dt, that's the thing I want to work out. Starting with dV by dt, what would I need to multiply it by? Well, I need to introduce dA, and I need to cancel out dV. So that chain rule there would give me dA by dt. So now I need, this tells me I need a formula for A in terms of V. Now that's going to be quite tricky. What we have actually got is area and volume in terms of radius. That's on your formula sheet. So we're going to need to take a middle step here that helps us to link the A and the V together. Let's start on that middle step. So the volume formula for a sphere is on your formula sheet, and that is 4/3 pi r cubed. The area, the surface area for a sphere is 4 pi r squared. Now, if I was to differentiate each of those, we're differentiating with respect to r because that's the variable that we've got in there, the radius. So differentiating the v term, we will have 4 pi r squared, and differentiating the a term, we have 8 pi r. Now, the reason we do that is I can now combine both of those to make dA by dV, remembering that that's what we're trying to get to, a dA by dV, to put it into our equation. So this here, I can make dA by dV by creating dA by dr multiplied by dr by dV, and then the r's would cancel out and we'd be left with dA by dV. dA by dr we just worked out was 8 pi r. dr by dV, well, we have dV by dr just here, so we want to flip that over. We'll times it by 1, hang on, 1, whoa, my screen's going all over the place. Here we go, hang on, 1 over 4 pi r squared, and that will cancel out to, the pi's are going to cancel, 8 over 2 simplifies, 8 over 4 simplifies to 2, the r over r squared will simplify to being over r, so that's 2 over r. Okay. We're not too far off of being able to get a solution now. Next step, let's go back to what we were trying to work out here. So the dA by dt is going to be dV by dt, which is 300, times dA by dV, which we just worked out over here as being 2 over r. So that simplifies to 600 over r. Let's just tidy that up. Okay, back to the question to check for some information. We want to know the rate that it's increasing in when it reaches bursting point, and that happens when the area is 7,500. So when the area is 7,500, we want to work out dA by dt, but the problem is we can't put it straight in because dA by dt is in terms of r and not in terms of a. So we need to work out the radius at that point. So surface area is 4 pi r squared, and we're setting that equal to 7,500. So r would be 7,500 divided by 4 divided by pi, and then square root. And we get 24.43. So then dA by dt at that point will be to do 600 over 24.43. So 600 divided by that answer is 24.56. And we'll just check on the units. Our area is in centimeters squared, and the time was in seconds. So it's centimeters squared per second. And there it is all on one page. Now, you did have an achieved mark available in here. That is at this stage just here. So that got you an achieved if you could get as far as that. The merit was for getting up to this point here of the 600 over r for dA by dt. Okay, on to integration. We've got a classic example of Newton's law of cooling here. If you're not sure about that, I do have some videos on particular applications of differential equations. It's towards the end of the integration playlist from my homepage if you want to go and review those. Okay, there's some helpful stuff with those applications of differential equations, things that will help you to memorize and be able to skip a few steps as we go through this. Okay, so the first part is we want to write down a differential equation to express the sentiment that's being given here. So let's just go through that. We've got the room's temperature remains constant at 18 degrees. So that means that the ambient temperature is 18. So I do that as T with a little suffix of A. The rate at which the temperature of the coffee changes at any instant is proportional to the difference between the temperature of the coffee and the room at that instant. So that means the rate at which the temperature changes over time, so that's dt by d lowercase t, is proportional to, so that's always equals k, the difference between the temperature of the thing and the temperature of the room, which is 18. Then on part 2, we've got some more information. We're going to solve the differential equation. So let's go to having that differential equation is kt minus 18. Now you can separate the variables, integrate both sides, and you will get down to an equation that is that T is equal to T of the ambient temperature plus the initial temperature, which I'm calling T0, minus TA e to the kt. Now to get from this step to this step is a process that you don't need to show all of the steps. You can memorize that that type of equation goes to this type of thing. The way to get from one to the other is by doing separating variables, integrating both sides, and you'll get to something that is equivalent to this, but you can memorize these to help save yourself a little bit of time. If you're not sure how I got from one to the other, go look at the videos on applications of differential equations. Okay, so let's put in the things that we have from our context. So the ambient temperature is 18. The initial temperature is 65. And we put in the 18 there, e to the kt. So the temperature of the room plus the difference in temperature multiplied by e to the kt, because we had this k involved here, a constant we need to work out. Now we're going to use the other information in the question to work out the missing pieces. So when the time is 2, we have a temperature of 62. Okay, so if we in fact, I'm going to just simplify this a little bit more first because we've got that subtraction. We may as well do that. So 65 minus 18 is 47 e to the kt. Okay, when T is 2, we have the temperature equals 62. So 18 plus 47 e to the 2k is equal to 62. So we can use that to work out e to the 2k. That will be 62 minus 18 and divided by 47. I'm actually going to leave that as a fraction. So 2k is equal to the natural log of 44 over 47. So k is equal to half of that. So let's go with natural log of our answer and then divide it by 2, which is minus 0. I think I've done that wrong. Hold on. 44 divided by 47. Natural log of that and then divide it by 2. I don't know what is going wrong, but that's not what I worked out earlier. Okay, I think I'm losing my marbles. Just going to try that one more time. Okay. All right, let's just carry on. I'm hoping that this is going to come out to the right answer. Maybe I just wrote something down wrong earlier, but let's carry on as we were. We've got k is half the natural log of 44 over 47. Now, if we pop that into the last piece of this, which is to work out when can he drink his coffee, which is when it gets to 54. So for the temperature equal to 54, we want 54 is equal to 18 plus 47 e to the half natural log 44 over 47 times k. Oh, sorry, times t. And we're going to work out what t is. So 54, take away 18. Then we divide by 47. Then we will do the natural log of that. Well, let's just write down what we've got so far. So we'd be left with e to the half natural log 44 over 47 times t is equal to this 0.766 stuff. Take log of both sides, so half natural log of 44 over 47 times t will be equal to e to the 0.766. So we do that raised to that, and we've got 2.15. Okay, now times that by 2 to get rid of the half, and divide it by natural log of 44 over 47. That should be a 47 just there. And it has gone really, really wrong. Okay, I'm just going to go back to this stage here. I think I must just be typing something wrong into the calculator right now. When I was doing this on this calculator by hand, these numbers worked out. So I'm just going to check that now. 44 divided by 47. Okay, bear with me. Okay, I'm going to write down the answers that I had earlier. So this came to 0.468 of working out what k is. So this was 0.468 times t. So then if we were to do 54 minus 18, I think I'm just going back to this calculator. So 54 minus 18 then divide it by the 47. So we have e to the 0.468t is equal to 0.766. So 0.468t is natural log of 0.766. And divide by 0.468. Okay, I do not know where it is that I am going so wrong with this. And I think, so I got down to this being like this, and then I got to the answer of t is 8.08 minutes. And I don't know if it's because I am tired or the pressure of being live. I'm making a mistake somewhere. I'm not seeing it. So if you want to be patient with me and stick around, you're welcome to. I'm just going to go back and work through what it is that might be going wrong here. 62. So at the moment, I'm going to go back to this line just here. 5 by 47. It's 44 over 47. E to the 2k is equal to 44 over 47. Natural log of that What is going wrong? Okay, I'm going to step it back quite far. We're just going to go through this back to here. Apologies, because I just keep making the same mistake. So let's go back a stage. Back to our original equation. I'm going to take you through the steps fully instead of relying on the memorized part. So bring the t over to the left-hand side. We've got 1 over t minus 18 dt is equal to k dt. We will integrate both sides. If we integrate 1 over t minus 18, we get the natural log of t minus 18 is equal to kt plus c. Now, what I was using before was to then do e of both sides t minus 18. So if I was to do each side raised to the power of them, then I would get oh, I think I see where I made a mistake on the previous thing. I think I might have remembered this bit wrong. So that would be a e to the kt plus c. A e to the kt. Okay, let's go with doing it in log form. So back to the information in the question. When it was poured, it was 65 degrees. So when t equals 0, we have natural log of 65 minus 18 is equal to k times 0 plus c. So c equals log of 65 minus 18, which is 47. Now, when t equals 2, we have natural log of t minus 18. Well, t when we're 2 seconds in, was it 2 seconds? No, 2 minutes in, then we've got 62 minus 18 is equal to k times 2 plus natural log of 47. So from there, k will be, let's go with log 62 minus 18. Oops, didn't mean to do that. 62 minus 18 is 44. Minus log 47. And, oh, that was 2k. So this will be a half of log 44 over 47, which is what I got the first time round. I wonder if I was just inputting it into the wrong piece by mistake. Okay, so that's k is equal to half of 2k equals that, so k equals half of natural log 44 over 47. Okay, now when the temperature gets to drinkable was, what was that, 54, I think it was? Yeah, 54. We'll have back to this equation up here, natural log of 54 minus 18 is equal to half natural log 44 over 47 times by t plus natural log 47. Okay, 54 minus 18 is 36. So natural log 36, subtract natural log 47, then we'll times it by 2, then divide by natural log 44 over 47, and we get t equals 8.08. So that was just unpacking each step within there. So 8.08 minutes. I have no idea what I did wrong the first time round. You guys probably can check it and see. There's probably something really obvious that you'll be able to see what it was, where I was going wrong on that first go through. But that is the right answer. The other thing to kind of maybe take some comfort in the mistake that I did the first time round was how you can spot that your answers aren't correct. And I was looking at the answer that I got previously, and it just did not make sense in the context that we were talking about. It wasn't going to fit the situation here of how long it's taking for that cup of coffee to cool down. So that's always a good check to do at the end, especially with these contextual questions, that you check and make sure that your answer actually makes logical sense. Otherwise, you need to go back and unpick where you've made the mistake. And sometimes, like this one today, you need to go all the way back to the beginning to make sure that you actually can work it through properly, and perhaps even try a slightly different route to the answer to make sure that you get to something that is sensible. So apologies, it took a little longer to get to it on that last one, but we have still done 3 excellence questions in less than half an hour, which is pretty good going, especially considering that I made quite a significant error on that last one. But that's some encouragement for you to be able to get 3 excellence questions done on 3 papers, and then multiply that by 3. You got 3 hours to do these things in the real exam, so that's plenty of time. That was about half as long as we needed to be able to do everything within the time frame that you have. So if you are going for excellence, practice heaps and heaps of excellence questions. They often come up in very similar settings as you've seen with these ones. These are pretty standard examples of excellence questions today. Do the merit ones too to give you that backup, but it is top-down marking. So if you get the excellence right, you will get the excellence points for that question, regardless of whatever has come before it on that question. With that, if you do make mistakes, there are points along the way to get your Achieve Merit and Excellence. On this one, in the mark scheme, it was to do the correct differential equation and integration. So it was getting down to this point here, got you an achieved. The correct integration with the general solution and logical working to find a correct value of k, that was your merit. And then, of course, excellence for getting all the way to the end. Okay, no questions coming through on the chat. I'll just give it a minute or two for the time delay between me speaking and what appears for you on YouTube. If you do have anything you want to ask, just pop it in the chat. Otherwise, I will see you next time. I'll post some more questions for tomorrow's live.